Hey guys, this is Ganjer V. Pagunahon II, and I'm here to teach you about the application of derivatives, specifically about the related rates. First things first, what is application of derivatives? According to Brightstorm, applications of the derivative identifies was that this concept is used in everyday life, such as determining concavity, curve sketching, and optimization. What is related rates? In differential calculus, related rates problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. The rate of change is usually with respect to time. Problem on the related rates is this. A person who is 6 feet tall is walking away from a lamppost at the rate of 40 feet per minute. When the person is 10 feet from the lamppost, his shadow is 20 feet long. Find the rate at which the length of the shadow is increasing when he is 30 feet from the lamppost. So this would be the scenario of the problem. I will draw the situation of the said problem. So there is a person who is 6 feet tall. Suppose this is the person. Which is 6 feet, and he is walking away from a lamppost which the height has not been set in the problem, and it said there that when the person is 10 feet from the lamppost, his shadow is 20 feet long. So this is the person, and this to the lamppost. When he is 10 feet away from the lamppost, the shadow of the person is 20 feet, right? So this is the lamppost. So technically, the shadow is here at the opposite side of the lamppost. So 20 feet. It's just like a triangle, similar triangles. Oh, look at this. So it's just like a similar triangles. This is the lamppost. Lamppost. So after that, we have to organize the given information. So dx over dt is equal to 40 when x is equal to 10 and s is equal to 20. So our goal is to find ds over dt when x is equal to 30, right? To set up a ratio of similar triangles, since drawing earlier shows that the relationship between the given data of the problem is just like a similar triangle. So the formula will be x plus s all over h is equal to s over 6. The x plus s all over h is the bigger triangle equated to this. Since it is a similar triangle, it is equated to s over 6, which is the smaller triangle. So this is the smaller triangle, this is the smaller triangle, and this is the bigger triangle, the combination of the two. So for continuation, since the height of the pole is a constant, we solve for h by using that x is equal to 10 and s is equal to 20. So we just need to substitute 10 and 20 to x and s in order to get h. So x equals to 10 plus Since S is equal to 20 over H is equal to 20 over 6. And add the 10 and 20 is equal to 30 over N. This is equal to 20 over 6. Cross multiply. 6 times 30 is equal to 20N. 6 times 30 is equal to 180. 20N in order 20H. I mean H. This is H. Sorry. This is H. 20H. So in order to get H, we need to divide the 20 both sides. 20. So H is equal to 90. 9. I mean 9. So H is equal to 9. So after getting H, now we need to rewrite our original ratio equation with the constant height solved for. So x plus s all over 9. This is 9. And is equated to s over 6. The 9 is the h earlier. So 6x plus 6s cross multiply is equal to 9s. 6x is equal to 9s minus 6s. 6x is equal to 3s. Differentiate both sides with respect to t and solve for ds over dt. So this is the final step, guys. So 6 times dx over dt is equal to 3 times ds over dt. So after that, 6 times 40 all over 3 is equal to ds over dt. So 6 times 4, we can minimize the 6 into 2, and 3 will become 1. So 2 times 40 is equal to 80 ds over dt. So our ds over dt is equal to 80 feet per minute. So the rate at which the length of the shadow is increasing when he is 30 feet from the lamppost is 80 feet per minute. That's it.